This is Dr. Danish Nisar, Associate Professor at the Center for Advanced Studies in Engineering, Principal Investigator of the 5GSTR project, and Senior Member Technical at the Center for Advanced Research in Engineering, GAIL. Welcome to this tutorial on evolution of direct RF sampling technology, recent advances, challenges, and the road ahead. In today's tutorial, we are going to learn about the RF front-end fundamentals, what are their primary tasks and requirements, what have been the various approaches to fulfill those requirements, and what has motivated the industry to move towards the direct RF sampling technology. Towards the end, we are going to have a look at some of the latest developments in the field of direct RF sampling. So let's begin. Radio frequency front-end. The RF front-end forms an integral part of any wireless communication transceiver because it performs the primary task of translating from the carrier frequency to the baseband at the receive side, and in the transmitter from the baseband to the desired carrier frequency. Sometimes this process is done in two steps, and in those cases we use an interim frequency. The baseband signal is first converted to an interim frequency, which is then referred to as an intermediate frequency, commonly referred to as IF, and then the RF front end converts this IF frequency to the desired RF frequency. And similar process happens also in the at the receive side in down conversion. The radio front end might receive the signal from the desired carrier frequency and convert it to an intermediate frequency, IF frequency, and then that IF frequency is further down converted to the baseband. But besides this primary task of frequency translation, the RF front-end performs some further tasks, and these include the signal amplification in transmit and receive paths, possibly for power control and variable gain requirements. So power control is a functionality at the transmit side where we need to adapt the output power of the transmitter according to the channel requirements or system requirements. And in the receive side, there is a crucial task of variable gain amplification, where the purpose is to amplify the signals strongly, which are very weak, and on the other hand, if the signal received is already strong, it needs to undergo a small amplification. Secondly, the RF front end also performs filtering to remove any unwanted spectral components from the signal. These spectral components might be there already as they are captured from the antennas, or might be generated as part of the RF front-end operations, as we are going to see. And finally, another important task of the RF front-ends is to counter any distortions that are produced in the above steps. So during the process of frequency translation, during the process of amplification, or during the process of filtering, there are often some distortions produced that need to be suppressed and countered. And now we say that in order to fulfill these various tasks that have been mentioned above, there exist various architectures for RF front-end design. And we will start with a discussion of these functionalities. But before we go into this, I would like to present some very fundamental facts as a refresher. Number one is that multiplication in time domain corresponds to convolution in the frequency domain and vice versa. This is something that you must have learned in the courses of signals and systems, that if you do multiplication of two signals in time domain, that corresponds to convolution in the frequency domain, and the other way around. If you do a convolution in the time domain, then the corresponding Fourier transforms or the corresponding spectra, they get multiplied. Another important fact that will be useful for this tutorial is that the spectrum of a complex signal is possibly asymmetric about zero frequency. So if the signal that we are talking about is complex, then we may have a spectrum that looks something like this. There is something asymmetric about the zero frequency. But once we talk about real signals, the spectrum is going to be conjugate symmetric about the zero frequency. And an example for that would be as follows. So this spectrum that we have drawn now, it corresponds to a conjugate, has a conjugate symmetric shape, which reflects a signal that is real valued. The third fact that I would like to talk about is complex conjugation in time domain corresponds to conjugation and flipping in frequency domain. So if you have a signal x of t and you take complex conjugate of this signal, then the corresponding Fourier transform is not only complex conjugated but is flipped in frequency. And the fourth fact that we will be using very often in this tutorial is that the spectrum of this signal exp j 2 pi fct, so it's a complex exponential with the argument 2 pi fct. The Fourier transform of this has an impulse at fc, which is then referred to as the center frequency or the carrier frequency, and the spectrum of cosine and sine are basically a pair of impulses at plus minus fc. So I repeat, the complex exponential e power j 2 pi fct has got a Fourier transform that looks something like this. It has got an impulse at fc. The Fourier transform of sine and cosine are a pair of impulses at plus fc and minus fc. And here I would like to mention that you may like to pause here and refresh these fundamental concepts before we proceed further. Now let's talk about the frequency translation task in RF frontends. So this is what we said is the fundamental task that needs to be performed at the radio frequency frontend. It needs to convert at the transmit side the signal from the baseband to the desired radio frequency or intermediate frequency. We say desired RF or IF. And the diagram here on the left side shows this process. A signal that lies in the baseband, it is being converted to RF or IF frequency. In order to understand this better, let me say that the two branches that you see here, this one and this one, correspond to the real and imaginary part of a possibly complex signal. If the signal is just real valued, the imaginary branch goes away. But if the signal is complex valued, and we said that the baseband signal that is complex would have possibly a spectrum that is asymmetric, that needs not to be symmetric about the zero frequency. So let's consider a signal that is complex. We say that st consists of two parts, si of t plus j times as q of t, where si and sq reflect the real and imaginary part of this complex baseband signal. The subscript I and q, as we will later see, refer to the term in phase and quadrature phase. And this is evident also in this diagram here, because the in phase branch, the upper branch, is being multiplied by the cosine of 2 pi fct or 2 pi of any carrier frequency, and the lower branch is being multiplied by the quadrature part of that carrier, so it's being multiplied with sine of 2 pi fct, and then the two terms are being added together to produce a signal which we say lies at the desired center frequency. In order to understand this better, I would like to do this simple mathematics. We say that s of t consists of sit plus j times sqt, and the operation that you see here on the block diagram on the left side can also be represented in the complex domain as follows. We have the signal s of t. We can multiply this signal with e power j 2 pi fct, and whatever we get, we take the real part of it, and that signal is x of t. And now let's examine what happens in the frequency domain once we do this multiplication, s of t getting multiplied with e power j 2 pi fct. Let's say this is the spectrum of s of t, so we label this as s of f. We also draw the spectrum of the complex exponential. The complex exponential, as we mentioned earlier, has a spectrum that is just an impulse at fc. And now, because of the fact that we are doing a complex multiplication in the time domain, we basically need to do a convolution in the frequency domain. And what happens as a result of this is that we get the spectrum that looks like this. This signal getting convolved in the frequency domain with this impulse would simply mean that we will get the same spectrum shifted here to the desired fc, the center frequency. And this basically corresponds to the part until this step. What happens next in this block diagram is that we take the real part of this signal. The real part basically corresponds to taking a complex signal and adding to it the complex conjugate of it, and then dividing it by 2. In the frequency domain, that would basically correspond to flipping of this spectrum and then adding the 2, taking the complex conjugate and flipping this spectrum along the frequency axis, and then adding the 2 to obtain the resulting spectrum at the output. So if we want to draw the spectrum of x of t, the flipped version of the spectrum will also be superimposed. And that will be the spectrum of the signal x of t. And we see that this process that you see here on this slide, on the left side of the slide, basically corresponds to this diagram, where the same signal, the real and imaginary parts, are being multiplied with cosine and sine of 2 pi fct, and then they are being added together. And you can readily see that complex exponential, which can also be written as cos of 2 pi fct plus j times sine of 2 pi fct. If it gets multiplied with this complex signal that you see here, and then we take the real part of this, that would correspond to the term si of t times cosine of 2 pi fct minus, because j times j is minus 1, sq of t sine multiplied with sine of 2 pi fct. And this is exactly the operation that is being performed on this in this block diagram. So we see that this is a fundamental operation of RF frontend. Once it wants to convert a baseband signal to any desired IF or RF frequency, it needs to do this type of operation. And we call this type of operation as IQ mixing, because there is a local oscillator that produces a particular center frequency. We generate two quadrature components of this carrier by introducing a phase shift of pi by 2 in one of the paths, and then we multiply them with the in phase and the quadrature phase part of the complex baseband signal, and then we add them together to obtain the real signal that needs to be passed on to the further subsequent blocks. The diagram on the right shows the converse operation. Here we want to convert the RF or the intermediate frequency to the complex baseband signal. And the operation that you see here can also be written in the complex domain as follows. So we have the signal x of t. It gets multiplied with e power j 2 pi fct with a negative sign here, e power minus j 2 pi fct, and then we apply a low pass filter to produce the signal s of t. And to see how these two block diagrams relate to each other and how do they achieve this task of converting the signal from the RF or IF frequency to the baseband, let's have a look at the Fourier transforms. First of all, we plot the spectrum of x of t, which is basically a signal at fc, at plus fc and minus fc. What we do next is multiplication in time domain. The multiplication is being done with e power minus j of 2 pi fct. The Fourier transform of this signal is as follows. It's basically an impulse at minus fc. Now, recalling that multiplication in time domain corresponds to convolution in the frequency domain, what we get as a result, the resulting spectrum that we get looks as follows. So this upper spectrum gets convolved with the lower spectrum, and the result will be that the two spectral versions at plus fc and minus fc will now get shifted around minus fc, leading to one spectrum coming at 0, and the other spectrum will move to 2fc minus 2fc, and it will look something like this. And the next operation that we apply here is the low pass filtering. The low pass filter simply removes the frequency component at 2 Fc, and eventually the output that we get as a result of this operation is the desired spectrum at 0 frequency. So we are able to recover to down convert the signal that was located at the carrier frequency Fc down to the baseband. And the same operation that you see here in the complex notation is reflected on the right side of the slide in an expanded form. The signal that we get is being multiplied with two quadrature carriers, the local oscillator producing the carrier producing a signal e power minus j2 pi fct is being realized with the help of the local oscillator by introducing a phase shift of pi by 2 in one of the branches. The two signals are then multiplied in both the branches to produce the real and the imaginary part. The low pass filter then removes the component at twice the carrier frequencies, and the result that we get here at the output is basically the same complex baseband signal that we had here. So this process of baseband to RF or IF and then RF or IF to the baseband are basically the converse operations of each other, and you can well imagine that the operation that takes place at the transmit side is this one, where we need to convert the baseband signal to the RF or IF frequency, and on the other hand at the receive side we need to convert the RF or IF signal to the baseband. What we note is that this process of frequency translation in RF frontend requires basically a pair of quadrature carriers, and by quadrature carriers I repeat we mean carriers at the same frequency but 90-degree out of phase from each other, and a filter at the receive side. Now proceeding further in this task of frequency translation, we note that if we are going for an intermediate frequency approach where the baseband signal is being converted first from the baseband to an intermediate frequency, in those cases there needs to be an extra step converting a real valued IF signal to the RF signal. And similarly on the receive side, if we are showing you here a block diagram for converting an IF signal to the baseband, the first step of converting an RF signal to an IF signal, both real valued, is left to be discussed. And that is what we discuss here, the frequency translation from RF to IF or vice versa. So on the left side you see the block diagram, which is a fairly simple block diagram for converting a signal from the IF frequency to the RF frequency at the transmit side, and the counterpart is shown here on the right side where the RF signal is being converted to the IF frequency. Now what you see in this block diagram is as follows. We have the signal which is already at IF frequency. So if we draw the Fourier transform, it looks as follows. So let's say this is our FIF and minus FIF. The signal spectrum is being drawn in black color, and it looks something like this. It is being multiplied, this signal is being multiplied with the signal from the local oscillator. The local oscillator frequency is a sinusoid or a cosinusoid, and it would therefore have a spectrum that looks as follows. It basically has got a pair of impulses F at LO. And minus FLO. And once these two signals are multiplied here in time domain, the frequency domain spectrums get convolved. The result of this convolution would be as follows. You will get a signal at FLO plus FIF, which will be something here. It will be FLO plus FIF, and the spectrum would look like this. There will be similarly a signal FLO minus FIF, and that would be therefore a signal that appears here, FLO minus FIF, and the spectrum of this signal would look like this. And similarly, the contributions from this impulse on the negative FLO side, there will be a signal spectrum situated at minus FLO minus FIF, and it would look like this. And there will be similarly a signal minus FLO plus FIF, that would look something like this. And then what you see as a result, so this is the signal spectrum at this stage. What you see next is a high pass filter. The high pass filter is intended to remove the frequency components. So these frequency components will then be removed, and what we will be left with will be as follows. There will be a signal at FLO plus FIF, and correspondingly at minus FLO minus FIF, and the spectrum of this signal would be like this. So if you compare this transition from here to this stage, what you see is that we have achieved a conversion of the same signal spectrum from the intermediate frequency to frequency FC, which is FLO plus FIF, and that is the sum of the two frequencies. The center frequency of the signal, of the resulting signal, is the sum of the frequency of the local oscillator and the intermediate frequency. Now if we take a look on the other side, we are doing conversion from RF to the IF. There exist basically two sub-cases in this conversion from RF to the IF, depending upon the frequency of this local oscillator. If the FLO, the local oscillator frequency that you have here, is less than FC, the carrier frequency or the center frequency that is there in the RF, we call this as low side mixing. And on the other hand, if FLO is greater than FC, then we call this as high side mixing. And we can have a look at both these two cases in terms of the visually in terms of the signal spectra. So let's first consider the first case. Let me first of all draw the spectrum of the incoming signal placed at FC. Let's say we have this as FC, and correspondingly this is minus FC, and the signal spectrum is as earlier drawn in the black color. It looks something like this. And this incoming signal is being multiplied, as you see in this diagram, with the local oscillator signal FLO, and we are first considering this case where FLO is less than FC, and in that particular case the spectrum of the LO signal would look something like this. So this is FLO and minus FLO, two pair of spikes, because it's a real local oscillator signal that is being generated. This may be sine or cosine of 2 pi FLO t. Now the multiplication of these signals in time domain corresponds to convolution in the frequency domain, and we can have a look at the result of this convolution here. You can readily see that there will be a contribution at FLO plus FC, which will be falling somewhere here, FLO plus FC, and there will be a contribution at FLO minus FC, and FLO minus FC will fall somewhere here. Sorry, it will be FLO minus FC. So these were the contributions from this impulse, and now let's take a look at what will happen as a result of this impulse. There will be a contribution at minus FLO minus FC, that will be here, minus FLO minus FC, and there will be a contribution at minus FLO plus FC, which will move towards the positive side, and you will find basically a contribution here, minus FLO plus FC, and the resulting spectra would be as follows. So because of this impulse, you'll get this on the upper side, and here on the lower side this will be the spectra that you get, and then from the second impulse you'll basically get a spectra that looks like this. Now this is basically the signal spectrum that we get at this stage prior to any filtering operation. What we see next in this block diagram is a low pass filter. The low pass filter will basically remove these high frequency components, and what you will get will be basically the spectrum that is left here, and we will call this frequency as your intermediate frequency. So we have basically then converted the signal from the RF to an intermediate frequency, in this case of low side mixing. We have FIF equal to minus FLO plus FC, or put other way, we can call that FLO, the local oscillator frequency for low side mixing, needs to be FC minus FIF. Depending upon where we want our IF signal to lie at, we can select the local oscillator frequency based on the center frequency of the RF signal. Now the other case of this to be covered in this conversion from RF to IF is the high side mixing, where the local oscillator frequency is greater than that of the center frequency. Let's have a look at that case as well. Here again we draw the spectrum of the signal located at FC, let's say this is FC plus FC, and then we have got minus FC here, and the spectrum looks like this. What happens is now that we have a local oscillator whose frequency FLO is greater than that of FC. So let's say that we have FLO here and minus FLO appearing here, and the spectrum of the local oscillator will be the pair of impulses at plus minus FLO, and it would look like this. The multiplication in time domain would then correspond to the convolution in frequency domain, and the result of this convolution would be as follows. There will be a signal going towards FLO plus FC, which will be somewhere on the extreme right. I will write it here. FLO plus FC, and then there will be a signal FLO minus FC at minus FC, and because of the fact that FLO is greater than FC, we will basically have it somewhere here. So it will be a signal at FLO minus FC, and the signal will have this shape. And now these were the contributions from this impulse. Now let's have a look at the contributions from this impulse in the convolution process. There will be similarly a signal that moves towards minus FLO minus FC, which will be on the extreme left of this diagram, and then there will be a signal at minus FLO plus FC, which will be somewhere here. And the shape of the spectrum will look like this and this. And what you see next is again a low pass filter. The low pass filter will basically remove this frequency component, so these two frequency components will then be removed, and what will be left with will be the signal that lies here. And as you can see, we'll basically have, in this case, this will be our FIF. So FIF in the case of high side mixing is equal to FLO minus FC, or put other way, FLO in this case corresponds to FC plus FIF. So if you compare it with the previous case of low side mixing, you see that in this case the local oscillator frequency was supposed to be equal to FC minus FIF. In the other case, it is FC plus IF. So depending upon whether you want to conduct a low side mixing or high side mixing, the local oscillator frequency is plus IF or minus IF apart from the desired center frequency. Now the slide also mentions an important issue, which is the image frequency issue. The image frequency issue in the case of RF happens in the case of RF to IF down conversion. Whenever we want to convert an RF signal to IF signal, the image frequency arises. What it really means is as follows. Depending upon whether you have configured your RF front end to perform low side mixing or high side mixing, in case of low side mixing, it will be bringing a carrier signal to the baseband, but will also bring an FC dash, a signal situated at FC dash at some other carrier frequency, also to the same IF. To understand why this happens, let us look at more details by just focusing on this equation. For low side mixing, we have FC is equal to FLO plus FIF. So we are considering first the case of low side mixing, and we see that in this case FC is equal to FLO plus FIF, and this is basically from this equation here, FC is equal to FLO plus FIF. But we say that if we are using this low side mixing, another carrier frequency at FC dash gets translated to the same IF frequency by means of the high side mixing taking place. So the high side mixing, FC is equal to FLO minus FIF, and that simply means that we will have an FC dash which will be FLO minus FIF, also getting converted to the same intermediate frequency. Because of the fact that there is nothing different in high side mixing or low side mixing, it's just a matter of interpretation of whether your local oscillator frequency is less than or greater than FC. Once you're pursuing the low side mixing and converting your desired carrier signal at FLO plus FIF to the FIF, there is another signal FC dash which is FLO minus FIF, it also gets converted to the same intermediate frequency, and then the two signals reside on top of each other. At IF. And this is a fundamental problem in carrying out this process of frequency translation in two steps. Whenever you move the signal from RF to IF, not only your desired signal is converted to the IF, but also another signal at FC dash, which is spaced 2 times FIF apart from your signal of interest, also gets translated to the same intermediate frequency. And if that portion of the spectrum is non-empty, it is being occupied by some interfering signal, that is basically introducing distortion in your system. The same problem happens in high side mixing. It's just the other way around. In high side mixing, you're basically converting FC equal to FLO minus FIF to your intermediate frequency. This is your desired signal, and this equation is being written from this line here. FC is equal to FLO minus FIF, but while doing this process, there is another signal at FC dash which is FLO plus FIF being converted to the same intermediate frequency via the principle of low side mixing. And these two spectrum will again overlap each other at the same intermediate frequency, and again we see that the gap between the two frequencies FC and FC dash is 2 times FIF. So depending upon whether you have designed or configured your system to perform low side mixing or high side mixing on your desired carrier frequency, there is another signal that is situated 2 FIF apart from your desired center frequency, which is also getting converted to the same intermediate frequency. This frequency FC dash is referred to as image frequency. And any signal that is present at the image frequency corresponding to the local oscillator frequency settings needs to be filtered prior to this operation of RF to IF conversion. And we will be talking about this a bit later. Now, moving ahead, we have understood all the various basic fundamental operations of frequency translation. The frequency translation can happen in 2 steps. So baseband to IF, or the converse operation IF to baseband, is shown on this slide, and in the next slide we studied the process of the intermediate process, the IF to RF or RF to IF. And in doing so, these discussions, we have also understood that there is a problem of image frequency in the case of down converting from RF frequency to the intermediate frequency. If we go for a 2-step procedure, we are going to encounter this image frequency issue. Now let's have a look at the various practical RF front-end architectures and what are their pros and cons. We are basically going to have a look at 5 RF front-end architectures. The first one is conceptually the most simple and straightforward. It is referred to as the direct conversion or homodyne or zero IF transmitter or receiver design, in which there is a single step conversion from the baseband to the desired RF frequency, or the other way around, from the desired RF frequency down to the baseband. The second RF front-end architecture that we are going to talk about is the super heterodyne architecture, in which there is a 2-step conversion. The third one is multi-stage super heterodyne, in which there are more than 2 stages of down conversion or up conversion. The fourth one that we are going to talk about is digital IF super heterodyne. This is basically a variant of super heterodyne receivers or transmitters with the digital IF frequency. And finally, the 5th architecture that we are going to talk about is the direct RF sampling or direct RF synthesis platform that has been the main focus of this tutorial. All the architectures, I would say here, all the architectures basically achieve this same task of frequency translation together with necessary amplification, filtering and other measures as we discussed earlier, but they all have their pros and cons as we are going to discuss now. So the first architecture is, as I said earlier, conceptually the most simple. It's basically the direct conversion, also referred to as homodyne or zero IF architecture. This slide shows the block diagram of the transmitter of such a direct conversion architecture. It involves a single step conversion from baseband to RF signal. So what you see here is the baseband signal being generated by any digital modulation scheme is basically coming out from some digital signal processing platform. The first task that we need to perform here is to convert this discrete time signal or digital signal into an analog signal, and for that purposes we employ DACs. So these are basically the I and Q branches that we discussed earlier. After passing through the DACs, because DACs typically produce images at the integer multiples of their sampling frequencies, we need to pass this signal through a low pass filter to retain only the image, only the spectrum that is lying in the region of plus minus fs by 2, and ignoring all other parts of the, suppressing all other portions of the spectrum in other Nyquist zones. So this low pass filter, after this low pass filter, what we see is exactly the same that we saw on a slide earlier. This is basically an IQ mixer. The IQ mixer accepts two branches, the in phase and the quadrature phase. It is then using a local oscillator with a quadrature phase shift of pi by 2 to multiply the two branches and then add them together, one with a positive and the other with a negative sign. And this process basically, as we saw earlier, corresponds to the frequency up conversion from baseband to the desired center frequency. Finally, we have an high power amplifier, HPA, placed at the output of this IQ mixer. The purpose here is just to amplify the signal to a sufficiently high output power that is required for transmission over the wireless channel. Now, the advantages of this architecture include, besides being conceptually simple, it employs DACs that are operating at very low FS, and this is something, the benefits will get more and more clear as we move on and have a look at other architectures. The DACs in this architecture need to operate at the bandwidths determined by the baseband signal, not the IF or even the RF frequencies, so these are considerably lower. Secondly, the IQ mixer and low pass filters can be integrated into a single chip, and that leads to a monolithic integration possible of such a transmitter. And finally, the filtering requirements are much simpler here. There is only a low pass filter that needs to filter out the images at the integer multiples of DAC sampling frequency. The disadvantages, on the other hand, which make this approach practically not feasible, are quite relevant. These are the IQ imbalance. We are going to see what IQ imbalance means, but at this instant, let me just say that IQ imbalance simply means that if the in phase and the quadrature phase parts of the carriers are not exactly 90-degree out of phase, that is basically a phase imbalance, and if they are not having equal amplitudes, that is basically the amplitude imbalance. So IQ imbalance refers to both amplitude and phase imbalance of the quadrature carriers. The DC offset leakage, in case there is any DC component present in the I or Q branch, then the consequence of this DC offset is that this LO signal, the local oscillator signal, gets leaked towards the antennas and gets even radiated. So this leads to not only to the wastage of power, but also leads to distortions once it comes to the receive side. Flicker noise is a noise in CMOS technology which is proportional to the reciprocal of frequency. It is not white noise, so it has a power spectral density which is higher at a lower carrier frequency, at lower frequencies, signal frequencies, and it becomes negligible and buries under the noise floor, otherwise AWGN noise floor, at higher carrier frequencies. So it's basically relevant only at low carrier frequencies, and because of the fact that all the components in this architecture, right from the DACs, so all the analog components are operating until this point in the low frequency region. The signal is being converted, analog signal is being converted at baseband, it is being filtered and then fed to the IQ mixer. So all these operations, because of the fact that they are happening at low frequencies, add great amount of flicker noise. So despite being conceptually simple, the IQ imbalance issue, the DC offset leakage and flicker noise are the major hurdles towards this architecture. Correspondingly, the receiver side, where we basically achieve a single step conversion from RF to the baseband, is the counterpart of that diagram that you saw on the previous slide. In this case, you see that the received signal is being filtered and low noise fed to a low noise amplifier LNA, and after that there is a process that you have seen in the previous in the beginning of this tutorial, the process of down conversion from the RF to the baseband. It involves an IQ mixer again and a low pass filter. So this operation basically converts the signal from the RF frequency region to the low pass to the baseband signal, and once that is done, the signal is subjected to some variable gain, is fed to an variable gain amplifier, and this variable gain amplifier then feeds the signal to the ADC, which digitizes the signal, which basically samples the signal and digitizes it and passes on then to the baseband signal processing platform. The advantages of this architecture are no image reject filters are needed because there is a single step conversion, and we have seen earlier that the issue of image frequency arises whenever we are going to have heterodyne architectures. So there are no image filters needed. Another advantage, as I mentioned earlier, is monolithic integration, but the disadvantages remain the same. There is an issue of IQ imbalance. So if there is any imbalance in phase or in frequency or in amplitude, that leads to distortions. And why is that the case? The problem here is that the IQ mixer needs to operate at a range of carrier frequencies. So depending upon whatever is currently the active carrier frequency, it needs to be tuned to that particular carrier frequency, and it's difficult to maintain the phase and amplitude balance for a wide range of carrier frequencies. The local oscillator leakage is yet another disadvantage, flicker noise and second order distortions, because the signal is being brought to the DC to the baseband in the analog domain. There are any distortions, any second order distortions that produce a signal distortion near the zero frequency affect this architecture the most. Now let's move ahead and have a look at the second type of RF front-end architecture, which is the super heterodyne architecture. The super heterodyne architecture involves a two-step conversion from baseband to IF and then IF to the baseband. This is something which we have also discussed in the previous part of the tutorial. The frequency translation taking place in two steps. The transmitter side is shown here in this diagram. We again see a baseband processing platform producing I and Q branches. The signal is being converted to the analog domain via DAC. It is fed to the low pass filters, and then there is an IQ mixer, but the difference is that this is a fixed LO IQ mixer. The local oscillator frequency here is fixed because it needs to provide, it needs to convert now this baseband signal to a fixed intermediate frequency. And once that is generated, in the second step, we make use of the RF of the IF to RF conversion modules that we had a look earlier. It consists of a variable LO producing a sinusoidal signal at a local oscillator frequency that will eventually determine where the center frequency of the overall final signal lie, followed by an high power amplifier. Now, as you can see, the advantages are IQ mixer calibration. The IQ mixer calibration is because of the fact that if you need to operate the IQ mixer at a fixed LO frequency, we can do a lot of precise calibration in order to ensure that not only the amplitude but also the phase of the carrier signals at that particular LO frequency are precisely calibrated and will always be in balance. So the issue of IQ imbalance goes away. And the second advantage is same as the previous one. DACs are operating at low sampling frequency. The disadvantages, on the other hand, is that we are requiring multiple local oscillators, so there are at least 2 local oscillators and 2 mixers are needed. The bandpass filter is required, and flicker noise is still an issue because the signal is being converted to the analog domain. The baseband signal is being converted to the analog domain. It has 0 frequency components, and the flicker noise in this region is much higher as compared to the high frequency part. So overall, we see that increased part count, flicker noise are the major hurdles, and similar is its diagram at the received side. We again see a converse operation, 2-step conversion from RF to IF and then from IF to the baseband. There is similarly a filter and low noise amplifier at the first stage, followed by a filter, and this filter is written here as IR filter. This is basically the image reject filter, and we had a discussion earlier on, in fact being shown here, the issue of image frequency arises in all super heterodyne architectures because the conversion is being done in 2 steps, and besides your center frequency of interest, there exists other center frequency which is 2 FIF apart, 2 times the intermediate frequency apart from your desired center frequency, that also gets through. The purpose of image reject filter is to suppress this frequency as much as possible before this process of down conversion, to remove all the interference, because otherwise, if that is not applied, the interfering signal would simply get superimposed on your intermediate frequency, and there will be no post-processing possible to recover the original signal. So the image reject filter has to come before this process of conversion, which we saw earlier. It's basically the conversion from the RF to the IF, followed by a variable gain amplifier. The variable gain amplifier then adjusts the gain of the signal according to the filtered channel of interest. This is then followed by the second step of conversion. In the second step, there is simply an IQ mixer used again, but the difference is that this IQ mixer is running at a fixed local oscillator frequency because it's always using the same intermediate frequency. Once the signal is brought down to the baseband, it is fed to the ADCs, and then baseband signal processing is pursued. So if we talk about the advantages and disadvantages, number 1 is IQ mixer calibration is possible, and the issue of IQ imbalance goes away. Number 2 is that the gain is distributed at different stages, so we can achieve a higher amount of gain by using amplifiers at different stages. Leakage is suppressed by the IF filters, so the any local oscillator leakage will not be passed on to the baseband processing platform because of the intermediate frequency filters, which remove any DC component present at this stage. The disadvantages, on the other hand, is that in order to achieve this image rejection, we need to have an high Q filter. High Q basically means a filter that has to have a sharp transition band response relative to its center frequency. So because of the fact that FC, the center frequency, is quite high as compared to the intermediate frequency, and this particular image reject filter needs to suppress the interfering signals as close as 2 FIF apart from its center frequency. The increased part count and flicker noise are the other disadvantages, and that makes us move to explore other possible architectures as well. Now the next 2 architectures that we are going to talk about are basically the variants of the same super heterodyne architecture. This is the multi-stage superheterodyne architecture. As the name implies, it involves more than two steps in conversion from RF to the baseband at the receive side. Typically, it's of use at the receive side, and the motivation can be explained as follows. It involves two IF stages, and first IF is typically even higher than the actual center frequency, and then there is a second IF which is much lower and closer to the baseband signal. What is the main motivation can be understood from this diagram of the superheterodyne architecture. The superheterodyne architecture needs to have these two filters, the image reject filter and the channelization filter at IF. The image reject filter, one of the disadvantages was that the high Q image reject filter is difficult to realize. If we have an intermediate frequency that is not high, then twice the intermediate frequency is also a small offset from the center frequency, and which imposes sharp constraints on the design of IR filter design, image reject filter design. What we do therefore is to have the first IF quite high, that allows you to have the IR to image reject filter designed easily, because the Q factor decreases. The twice the intermediate frequency, which forms the potential image frequency, is too far away from the center, from the desired center frequency, and that allows an easy realization of the image reject filter. But then the question arises, why not to simply choose a higher IF? Higher IF is not suitable because we need then to design also the channelization filter at IF frequency, which channelizes the desired signal only through at the IF stage. All the components beyond the channel of interest at the IF frequency have to be suppressed. And if the IF frequency is too high, then the design of channelization filter becomes too difficult. So the benefit or the motivation of this multi-stage superheterodyne architecture is that it uses two stages of IF. The first IF stage facilitates the design of the image reject filter. The second IF stage, which is closer to the baseband, facilitates the design of the channelization filter. But there exists some drawbacks. Increased part count is a major issue, because as you increase the number of stages, you need correspondingly larger number of IQ mixers or mixers. Similarly, local oscillators are increased, the amplifiers and bandpass filters are also larger. And the second problem is common to all the architectures that we have studied so far, flicker noise. Flicker noise will be distorting the signal, especially once it is being converted to the baseband in the analog domain. Nevertheless, multi-stage superheterodyne receiver architecture facilitates practical realization of superheterodyne receiver. So typically all the superheterodyne receivers that you will encounter in practice, they typically employ multi-stage superheterodyne conversion. The fourth architecture is also a variant of superheterodyne architecture. The difference is that now we have IF in the digital domain. IF part is implemented in the digital domain. So if we look at the transmit side, we will see that the baseband processing, from the baseband processing there is an upsampling, and then followed by a DDS implemented oscillator signal generated, introducing here a phase shift of pi by 2, and then these are processed before the conversion to the analog domain. So all this part is now implemented in digital domain. And because the intermediate frequency is generated right in the digital domain, we call this superheterodyne with digital IF. The main advantage that it achieves as a result is that flicker noise vanishes, because the signal, once it is being converted in the analog domain, it has no frequency component near the zero or the baseband levels. Furthermore, because of the fact that more and more components have been implemented in the digital domain, the analog part count is reduced. The mixer in digital domain does not have any impairments. So the issue of IQ imbalance, which happens in the case of analog IQ mixers, does not happen in the digital domain, because here the signal is being precisely generated by the DDS, a phase shift of pi by 2, and the amplitude balance can easily be retained in digital signal processing platforms. Remaining of the architecture remains the same. There is a DAC converting the signal to the analog domain, then it's filtered. Low pass filter is necessary to remove the spectral images at the sampling frequency of DACs. A local oscillator then converts this from IF to RF region. The bandpass filter is then needed to remove other undesired spectral components, and finally there is a high power amplifier. Now, what is the drawback of such an approach? The drawback of this approach is that, as compared to the traditional, the three architectures that we have seen earlier, the DACs and ADCs now that are needed need to support the signal spectrum, need to support the IF frequency. So if the IF frequency, if the baseband signal bandwidth was just 50 kilohertz or 100 kilohertz, and the IF frequency is around 20 megahertz, you need to have DACs and ADCs that are capable of handling frequencies at the IF level now. So this approach, but that drawback is nevertheless does not hurt us too much because of the advances in CMOS technology. So this is basically a pragmatic approach to RF front-end design that solves many of the problems. So super heterodyne with digital IF has been the state of the art for many decades now. Similar is the concept at the received side. IF stage is again implemented in the digital domain. We have a low noise amplifier, an image reject filter, a variable local oscillator to bring our signal down to the IF frequency, and the signal, after some channelization, variable gain, is then digitized. So all that you see here, all the IF processing is then done in the digital domain. Including the process of down conversion to the baseband, and this means that because the signal is being converted to the baseband in the digital domain, there is no issue of flicker noise, there is reduced analog part count, and the mixer in digital domain does not have those analog domain RF impairments. The disadvantages is the same. High speed ADCs are now needed to handle the digital IF frequency. Finally, the fifth architecture is the one that we are heading towards, the world industry is heading towards. This is the digital RF architecture. On the first slide, we are going to talk about the transmitter side. In this context, it's often referred to as direct RF synthesis, because the RF frequency is being synthesized directly without any multi-stage conversion, and is all being done in the digital domain. So we see that the baseband signal that we are producing here is first upsampled. It is then converted to the desired RF frequency by the means of DDS, and once the desired RF frequency is generated, it is simply converted to the analog domain and bandpass filter to remove the spectral images at any integer multiples and fed to the high power amplifier. As you can see, if you compare it from the previous architectures that we have seen, there is a significantly reduced analog domain part count. So we only have now a bandpass filter and a high power amplifier, and this reduced part count has direct implications on the no analog RF impairments, because most of the analog RF impairments arises from IQ imbalance from the mixers, which are not present altogether in this architecture. And another advantage, huge advantage in terms of practical implementations, is that because of the fact that all the RF frequency processing is being done in the digital domain, and there are no specific analog components tuned at particular center frequencies. The range of frequencies that we can achieve, the range of RF frequencies that we can achieve by means of this architecture are huge and almost unlimited, limited only by the sampling speeds of DAC. Ultra high speed DACs are needed to realize this digital RF architecture, but with the advances in CMOS technology, this is becoming more and more easily possible, and that explains why the industry is moving towards this digital RF technology. Conversely, if we take a look at the receive side, we call this as direct RF sampling because of the fact that the RF signal is being sampled directly without any down conversion to an intermediate frequency, single stage or multi-stage intermediate frequency conversion, and without the need of conversion to the zero or the baseband in the analog domain. All the conversion process of frequency translation is being done in the digital domain. So what you see here, we employ a filter and low noise amplifier, a variable gain amplifier, and then directly an ADC, which we often refer to as an RF ADC, to emphasize that this is an analog to digital converter that can have a very high sampling frequency, and it can basically digitize the RF signal directly. And once that is done, all the processing is done in the digital domain, and there is a single step conversion. In a single step, because the filters are being implemented in digital domain, the signal is being converted from the RF frequency to the baseband. It's being low pass filtered, down sampled, and then fed on to the baseband receiving platform. The advantages are the same: no analog RF impairments, no reduced part count, flexible RF ranges. The disadvantage is one, that we need ultra high speed ADCs in order to sample the signals directly at RF frequencies. But as I said earlier, this is becoming more and more possible with advances in CMOS technology. Now, because it is difficult to appreciate the benefits and advantages of direct RF architecture without having an understanding of RF front-end impairments, I would like to have a quick walk through the various RF front-end impairments that impact many of the RF front-end architectures that we discussed earlier. So these are basically the various components in RF. These are the various analog components in RF that lead to signal distortions and imperfections. And there are basically three categories of such RF impairments. Phase noise, which is specific to the local oscillators. So wherever you see a local oscillator in the diagrams, there is an associated phase noise being generated. Then there is an IQ imbalance issue. The IQ imbalance occurs only, it is specific to the mixers, IQ mixers, which are responsible for generating an appropriate phase shift and then mixing them with the incoming signal. And the third aspect that applies to in fact all the components in the analog RF domain is the non-linearity of the components. And detailed analysis of RF front-end impairments is crucial to the design of successful RF front-ends. So we will walk through them one by one quickly. Phase noise. Phase noise is basically an artifact of the local oscillator wherever it is present. In a multi-stage super heterodyne transceiver, there are a number of local oscillators present. Ideally, the local oscillator phase should vary linearly along time. So if we draw the phase over time, we should see a line like this depending upon the LO frequency. But the practical local oscillators exhibits jitter overriding the linear phase, and that can be expressed as something like this. Instead of truly rising linearly along time, they show some noise, and this has a consequence that if you see the overall spectrum, the spectrum does not look as sharp as this, but it has a skirt surrounding, so the spectrum just widens up and it looks more like this. And this is basically the phase noise that can be seen in the spectrum as well. The phase noise is typically expressed in the units of dBc per hertz. It's basically a power spectral density, but expressed with respect to the carrier power. How much is the phase noise at a given offset from the carrier? So you might have heard about terminologies like some dBc per hertz at offsets of 10 kilohertz from the carrier. Overall, the impact is that it raises the noise floor of the receiver and eventually therefore affects the signal that is being processed. The second RF impairment that we are going to look at is IQ imbalance. It is something specific to the quadrature mixers that we have seen in the previous block diagrams of various architectures. Whenever the I and Q branches are being mixed together by means of quadrature carriers at the transmit side or are being generated at the receive side, we use quadrature mixers. The quadrature mixers need to have the I and Q branches with exactly equal amplitudes, and the phases of the two component carriers, those going towards the I branch and Q branch, need to be exactly 90 degree out of phase from each other. The practical IQ mixers, however, often have imbalance in terms of amplitude and non-ideal phase offset between I and Q, and this happens primarily because of the fact that even though a practical analog IQ mixer, quadrature mixer, can be calibrated at a particular frequency, the calibration might not apply over a broad range of carrier frequencies at which the quadrature mixer needs to be operated at. So that is the reason whenever there is a variable local oscillator and the quadrature mixer needs to operate on a wide range of frequencies, the amplitude imbalance and the phase offset, non-ideal phase offset, do arise, and it leads to imperfections. What type of imperfection does it lead to depends upon the type of artifact. If there is only amplitude imbalance, we get a so-called rectangular constellation, as is shown on the diagram on the right. Instead of the blue ideal constellation, we get a tall constellation in red whenever there is an amplitude imbalance and the Q branch has a higher amplitude. Another possible artifact is the phase imbalance, and the phase imbalance, it can be shown mathematically that it introduces a skew in the constellation, and we get, instead of the ideal blue constellation, we get the red constellation, which is skewed towards the left. The third and the major category of RF impairment is component nonlinearity. Linearity implies a linear relationship between input and output, which means that doubling the input doubles the output. This happens for many analog RF components. This happens over a consistent range of signals, but once the input signal amplitude starts to increase, the component nonlinearity starts to be evident. And that is something shown here for a typical amplifier, for instance, which has an input power being fed into the amplifier and output power coming out of it. The input-output, the relationship between the input and output is linear up to a significant range of input signals, but then the output starts to drop from the ideal output. The observed output at the point at which it is 1 dB lower as compared to the expected output is referred to as the P1 dB point, and this P1 dB point is a quantitative measure to specify the point in terms of input power at which the component nonlinearity begins to be more and more evident. Besides the saturation in input-output relationship, another consequence of component nonlinearity is what we refer to as intermodulation distortions in harmonics. To understand why they happen, it's useful to consider a test signal that has at least two carrier frequency components, and for that purposes we typically consider a two-tone test signal that can be written as x of t equal to alpha 1 times cosine of omega 1 t plus alpha 2 times cosine of omega 2 t. So this test signal has two carrier frequencies, omega 1 and omega 2, and alpha 1 and alpha 2 control the relative amplitude of the two component carriers. Such a test signal, if it passes through a nonlinear device such that feeding x of t at the input, we get y of t at the output. For a nonlinear device, we can write down the input-output relationship as follows. Y of t can be given as beta 1 times x of t. So the input signal is scaled by some amplitude beta 1. If it's the case of an amplifier, it will be a number greater than unity, leading to some signal amplification. And this will be referred to as the linear term in the relationship. But there are terms that lead then to nonlinearity, and that would have different coefficients like beta 2 times x square of t plus beta 3 times x cube of t, and so on. Typically we consider nonlinearity models up to the third order. So beta 1, beta 2 and beta 3 are sufficient to characterize the nonlinear behavior of any device. And in presence of these coefficients, if we try to substitute the input signal x of t into this expression and then find out the output at various frequency that arises at various frequency components, so including the DC position at omega 1, at omega 2 and so on, we get to these amplitudes. This is a table that I have copied from the book of Tony Raufil, and you can find out this table in there, and it's basically a simple mathematical manipulation of this expression, putting in this expression into y of t and applying some trigonometric identities, and you will get to these expressions. It tells you that at omega 1, besides the desired component of beta 1 times alpha 1, which will be the desired behavior of any linear device, there are some nonlinear components. Similarly, at omega 2, not only beta 1 times alpha 2 is observed, but there are some components, nonlinear components there. Similarly, there will be some components present at the integer multiples of omega I, which will be referred to as the harmonics, and then there are some contributions at the summation or differences of various integer multiples of the two tone frequencies omega 1 and omega 2, and these are referred to as the intermodulation distortion. So we call this as harmonics, and the one that are appearing here are referred to as the intermodulation distortions. And all of these you will see have coefficients beta 2 and beta 3, and whenever the device is linear, that is beta 2 and beta 3 are both equal to 0, these nonlinear distortions, harmonics as well as intermodulation terms disappear, and also the term at DC disappear, and we will have only a term at omega 1 and omega 2, and that too only the one that are the desired terms, beta 1 times alpha 1 or beta 1 times alpha 2. So we define the components at integer multiples of input frequency are referred to as the harmonics. So this is one type of distortion that is produced. The components at sums and differences of integer multiples of input frequencies are referred to as the intermodulation or IM distortions. Looking closer, we will see that intermodulation 2 or the second order intermodulation are produced when the sum of the two integers m plus n absolute values is equal to 2. That is, m and n are both unity. In this case, the amplitude is solely determined by beta 2. As you can see here, the second order intermodulation distortion is determined by beta 2 times alpha 1 alpha 2. For simplicity, we will be now considering the case of alpha 1 being equal to alpha 2. So that is, both the tones in the test signal have equal power, but the analysis or the conclusions that we are going to derive will apply equally to all other scenarios as well. Now, once that is the case, it is fairly evident that the amplitude of the intermodulation distortion is completely determined by beta 2, and if beta 2 is a small number, this will be a small power at the output. The problem, however, is that beta 2 is the amplitude and the second order intermodulation distortion is given as beta 2 times alpha square. Unlike that, at the desired power, which is beta 1 times alpha. The difference is that even though beta 2 is a small number, if the input power is increased or if the value of alpha is increased, we can see that this power, the second order intermodulation power, grows to the square of alpha as compared to the linear of alpha. So that means on a dB scale, it grows twice as fast as the desired component power, and this is reflected here in this graph of input versus output. The fundamental power is reflected in this line, which increases at a certain pace. This intermodulation distortion, the second order intermodulation distortion, it is plotted with this with this line, and as can be seen, it is increasing at twice the rate of the fundamental input power, and then we can imagine that the two will intersect at a certain point, which is referred to as the intercept point IP2. This is basically a fictitious point because this intercept or intersection will take place probably at such a high signal power level that the component will start saturating even much before that particular power. But it is a useful way to characterize the amount of second order distortion, and that is why we say that the IP2, the x-axis at this intercept point, which is basically the input power, is referred to as the input intercept point for the second order modulation. It is typically expressed in dBm. And similarly, if we have a look at the third order intermodulation distortion, these are the intermodulation distortions for which the sum of the absolute of m and n is equal to 3. So frequencies like 2 omega 1 plus omega 2, 2 omega 1 plus minus omega 2, or 2 omega 2 plus minus omega 1 are basically those responsible for the third order intermodulation. If we take a look at the graph, at the table, we'll see that the third order intermodulation distortion are completely determined by beta 3, and On a closer examination, it will be revealed that they grow by this amount, beta 3 times alpha cube. And on a dB scale, that would mean that even though beta 3 is a small number, the rate at which the third order intermodulation grows will be thrice as fast as the rate of growth for the desired power. And that is what again leads to an intercept point. This would be a similar graph which will have an intercept point 3. That will be the intercept point between the fundamental signal power and the third order intermodulation distortion. The intercept point is referred to as IP3. It is also a fictitious point because the input power corresponding to this would not be observed in reality, the output, because the components typically saturate much before that point, but it is detrimental for all types of receiver architectures. While the second order intermodulation distortion typically leads to signal components that are omega 1 at omega 1 plus omega 2 or omega 1 minus omega 2. Omega 1 plus omega 2 are typically discarded away by high pass filters. The components at omega 1 minus omega 2 are more or less the components at near the DC level, and these DC level signals are bad for the direct conversion receivers, which are relying on direct conversion of the baseband, and some of the signal then gets distorted. The intermodulation 3, the third order intermodulation, however, is detrimental for all types of receivers, because any signal that contains two carrier frequencies, omega 1 and omega 2, that are fairly close to each other, will also have 2 omega 1 plus minus omega 2 or 2 omega 2 plus minus omega 1 within the same band, and that will be basically causing distortions in band. So that is detrimental for all receiver architectures. In order to avoid these types of intermodulation distortions, the IIP2 and IIP3 should be at least 20 to 30 dB higher than nominal input power. So we need to operate the devices at much lower values of these two intercept points, IIP2 and IIP3. Finally, some other characteristics of the RF frontends. Noise figure is the ratio of CNR carrier to noise ratio at the input versus output, expressed typically in dBs. It reflects basically the additional noise injected by the analog components, and all analog components typically add some degree of noise to the receiver circuitry, and therefore this is one of the other incentives to go towards direct RF sampling, because direct RF avoids the analog RF components that degrade the signal to noise ratio or carrier to noise ratio. The dynamic range typically refers to the strongest and the weakest, the range of the signal that the device can work with. The strongest and weakest signal that RF front-end can safely process. The weakest signal is determined by the noise floor, because signal levels below the noise floor are not going to be visible to the RF front-end and cannot be processed. The signals above the P1 dB point are similarly also distorted too much to be safely processed. The spurious free dynamic range, SFDR, is another important parameter of characterizing RF frontends. The weakest signal is again determined here by the noise floor. The strongest signal is the one at which the intermodulation distortions, these distortions rise above the noise floor level. So if the receiver noise floor at this level, the range of the input signal level at which the IM3 rises above the noise floor level is referred to as the highest possible signal level that can be safely processed, and that determines the SFDR, the spurious free dynamic range of the receivers. The specifications of these noise figure, IM2, IM3, dynamic range, phase noise parameters are key to a comprehensive quantitative analysis of RF front-end impairments. So these are all the impairments that have motivated the industry to move towards the direct RF sampling technology. But there are some challenges as well. The direct RF solves many issues, but there are some challenges associated with this, and it's useful to have a look at them to understand the limitations, to understand the key design aspects whenever we talk about the direct RF architecture. Number one is the reduced dynamic range in presence of strong interferers. Unlike the heterodyne or super heterodyne architectures where there are a lot of filters that reject the out of band signals, and therefore at the time of analog to digital conversion, the signal level is adjusted in a very precise manner to suit the range of ADCs with respect to your signal of interest. In the case of direct RF sampling, since we do not employ excessive filtering, there might be some strong interferers existing besides our signal of interest. So for instance, consider this case where we have the desired signal in green at F0, and there are some two strong interferers at F1 and F2. In order to be able to safely process the signal, in order to be able to directly sample this signal, receive signal at ADCs, we need to ensure that the gain is adjusted in such a manner that ADC does not enter into saturation because of these strong signals. So the gain cannot be high, because otherwise these strong signals may undergo saturation, and that saturations will lead to distortions in the desired band as well. And on the other hand, if the saturation of this signal is avoided, since the signal of interest is too weak, is too low, the effective number of bits that this signal encounters at the analog to digital conversion will be too low. So that effectively reduces the dynamic range of the RF ADCs in presence of strong interfering signals. The problem is not of much concern in a scenario like this, where the interfering signals are of moderate strength as compared to the signal of interest. So some degree of pre-filtering needs to be applied whenever we are using even the direct RF sampling. Now towards the end of this tutorial, let's talk about some of the latest developments in the field of direct RF sampling. We are going to see what are the latest SDR platforms with direct RF synthesis and sampling capability. First of all, Xilinx. Xilinx has been producing direct RF sampling platforms since 2018. The first generation of its RF SoC platforms had 8 DACs and 8 ADCs supporting direct RF sampling rates of up to 6 gigasamples per second. The current generation of Xilinx RF SoCs have up to 16 RF ADCs and DACs with 14-bit resolutions and sampling rates of 5 gigasamples for ADCs and 9.85 gigasamples for DACs. And that just means that if you are operating with first or second Nyquist zone of the DACs, you can safely operate this device to produce carrier signals with carrier frequencies as high as 18 or 19 gigahertz. Similarly, at the ADCs, with the sampling rate so high, we can safely process the signals not only according to the Nyquist sampling criteria, but also for those signals which have carrier frequencies like 12 gigahertz or so, can also be safely processed provided their bandwidth is not excessively large. So for all practical purposes, such RF SoCs by Xilinx can safely process signals in multiples of gigahertz. High density FPGA is also provided in these cores, quadrature core ARM for the application processing, and there is also a real-time processing unit, and these boards therefore facilitate large MIMO operations as well, because you have access to 16 ADCs and 16 DACs. So a 16 cross 16 system can easily be implemented on such a platform. Pentec is another big industry leader in this field. Pentec has been introducing the Quartz family of platforms. It is also based upon the Xilinx UltraScale Plus RF SoCs, and the generation that we have listed here has 8 RF ADCs and 8 DACs with 5 and 10 gigasamples per second. It has expandable I/O, so a number of interfaces are possible besides the SMA connectors for the RF signal transmission and acquisition. The direct RF, as you can see, can reduce the size, weight and power profile and improves flexibility and scaling. Then we have Texas Instrument. Texas Instrument chip AFE795046R has the capability of having 4 transmit and 6 receive antennas. 12 gigasamples per second DACs are there, 3 gigasamples per second ADCs are available, up to 2400 megahertz of instantaneous bandwidth capture is possible. It is also basically a compact direct RF sampling based platform, ideal for the next generation communication systems. Finally, Intel is also jumping into this domain and has been introducing FPGAs integrated with direct RF architectures. Up to 64 gigasamples per second sampling rates are supported with low power, less bulky and frequency agile platforms for military, radar, high-end test and wireless solutions are being provided by Intel as well. So let us summarize the take-home message of this tutorial. The RF frontends pursuing the crucial tasks of RF frequency translation form an integral part of all radio transceivers. The theoretical direct conversion architectures, which are conceptually the most simple and straightforward, encounter many practical challenges, and these include the DC offset leakage, IQ imbalance, flicker noise and other such artifacts that we have discussed in detail. The super heterodyne architectures have been the solution to this problem. The super heterodyne architectures proposed to achieve this frequency translation in two or more steps, and by doing so, by introducing an intermediate frequency step, they resolved some of the issues of the direct conversion transceivers and have been at the center stage for many decades. However, now with the advances in CMOS technology, high-speed DACs and ADCs are becoming reality. And direct RF synthesis and direct RF sampling are a direct consequence of this advancement. These avoid the nonlinear analog RF impairments. They reduce the part count, the maintenance cost, and the calibration cost, and provide vital flexibility for dynamic spectrum access, which means that you can access whatever region of spectrum you like without needing to retune or recalibrate the components, the analog components that have been installed in the RF frontend. And because of the compactness, they are also suitable for large MIMO operations. So basically, we are witnessing a paradigm shift from the classical RF frontend architectures to the direct RF architecture for next generation communication transceivers. With that, I thank you all for your attention and time, and I wish you all the best. I hope you all are having a great learning experience and at the IEEE 5G World Forum 2021. Thank you. Bye.